Late November, 1941. An Iceland harbour, somewhere north of Reykjavik. The sky turned black at 3 in the afternoon, the way it does that far above the Arctic Circle when winter tightens its grip. Wind screamed across the volcanic rock at speeds approaching 90 miles per hour, transforming the harbour into a cauldron of spray and fury. On the beach, a PBY Catalina flying boat that weighed 7 tons crumpled like tissue paper. The gale tossed it sideways, ripping aluminum skin from its frame, folding wings that had crossed oceans into twisted wreckage. Nearby, British Nissen huts that had housed troops since summer simply came apart. The corrugated metal panels tore free from their frames, tumbling across the landscape like enormous sheets of foil. Men scrambled from disintegrating shelters into the storm, seeking refuge anywhere they could find it. But scattered among the ruins stood a different kind of structure. Curved steel buildings, newer than the British huts, barely months old. The same hurricane-force winds that demolished everything around them howled over these arched forms and kept moving. When dawn finally came and engineers surveyed the damage, they found American Quonset huts standing practically untouched. Not undamaged, a few panels had dents, some windows had cracked, but standing. Functional. Still protecting the men sheltering inside. The question naval architects asked wasn't whether these buildings worked. The Iceland storm had answered that conclusively. The question was, how? How did a structure so simple, so lightweight, engineered in just 3 months by a team that had never designed military housing before, survive conditions that destroyed buildings designed by experienced British military engineers? If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The answer revealed itself not in any single innovation, but in a series of deliberate engineering choices that transformed what should have been a temporary wartime expedient into one of the most durable structures ever deployed at scale. The Quonset hut succeeded because its designers understood something fundamental about physics, something that ancient architects knew when they built Roman aqueducts and Gothic cathedrals. The arch doesn't just support weight, it redistributes force in ways that make a structure almost indestructible. March 1941. Naval facilities at Quonset Point, Rhode Island. The United States Navy handed the George A. Fuller Construction Company an impossible assignment. Design and produce a prefabricated building that could house troops anywhere on Earth, from the Arctic to the tropics, that ordinary soldiers could assemble without specialized training, that would withstand bombs, storms, extreme heat, and Arctic cold, and deliver the first units in 60 days. The Navy gave the Fuller team exactly 2 specifications. First, the structure must have an arched shape for strength and deflection of shell fragments. Second, it must be simple enough for untrained personnel to erect quickly. Everything else was left to the engineers. Peter de Jong, a Fuller Company engineer, and Otto Brandenberger, the company's only staff architect, led the design team. Brandenberger brought unusual qualifications to the project. He'd emigrated from Switzerland, studied architecture at the Zurich Technical Institute, and served as a sergeant in the U.S. Army. That military experience mattered. Brandenberger had lived in field conditions. He knew what soldiers needed, what they could tolerate, and what would fail when theory confronted reality. The Navy pointed them toward the British Nissen hut as precedent. Major Peter Nissen had designed it during World War I, a semicircular corrugated steel shelter that British forces used extensively in France. Simple concept. Bend corrugated iron sheets into a Turk, half-cylinder, bolt them to a steel frame, close the ends with wood. Thousands of Nissen huts provided shelter from 1916 through 1918, but Brandenberger's team identified serious problems with the Nissen design. It offered virtually no insulation, just 2 layers of corrugated metal with an air gap between them. The interior stayed brutally cold in winter and became an oven in summer. The curved walls meant beds, equipment, and supplies had to cluster in the center, wasting floor space near the edges. Assembly required skilled labor because the corrugated panels needed precise alignment, and the design provided minimal natural light, making the interior dark even during daytime. The Navy wanted improvements, not a copy. Brandenburger's team kept the arch shape, but redesigned almost everything else. The critical innovation came in the structural system. Instead of covering a frame with corrugated panels, they engineered the building as a series of interlocking, steel arches. Each arch section was fabricated with pre-drilled holes that aligned perfectly with adjacent sections. The arches created a self-supporting skeleton that didn't require internal columns or complex bracing. This design choice solved multiple problems simultaneously. The arch form itself provided inherent strength. When wind pushed against the curved surface, the force distributed evenly around the entire structure instead of concentrating at corners or flat surfaces. When snow accumulated on the roof, the weight compressed the arch, but the arch converted that vertical force into horizontal thrust that pushed outward at the base. As long as the base connections held firm, the structure could support enormous loads without bending or buckling. The Navy's requirement for shell fragment deflection led to the arch shape, but that arch delivered benefits far beyond protection from shrapnel. The curved form had no flat surfaces for wind to grab, no corners where stress could concentrate, no roof peaks where snow could accumulate unevenly. Physics worked in the structure's favor. Brandenburger's team then tackled the insulation problem that plagued the Nissen hut. They developed a sandwich panel system using 3/16-inch masonite, pressed wood for the interior lining, a 1-inch layer of wood fiber insulation, and corrugated galvanized steel panels for the exterior. Steel clips attached the masonite to the arch ribs, creating an air gap that provided additional thermal protection. This assembly method meant workers could install insulation during construction rather than adding it afterward. The system wasn't perfect. Metal conducted heat more efficiently than wood, but it provided dramatically better thermal performance than anything available in a portable military structure. The ventilation design prevented the interior from becoming a condensation-dripping nightmare. Ridge vents ran along the roof peak. Louvered openings in the end walls allowed air circulation. In tropical climates, screened ventilator shafts could be added. The system worked passively, requiring no mechanical equipment, using natural convection to move air through the structure. The end walls presented unique challenges. They needed to provide access through doors, allow natural light through windows, yet maintain structural integrity. The team designed prefabricated end panels from plywood with door frames and window openings already installed. Different end panel configurations accommodated different climates. Screened panels for tropical use, solid insulated panels for Arctic conditions. The flexibility allowed one basic structure to function across every climate zone Earth offered. The floor system used tongue and groove plywood panels, supported on a raised metal framework. This solved another Nissen hut weakness. The original British design often placed structures directly on the ground, leading to moisture problems and cold floors. The raised Quonset floor stayed dry, provided insulation, and in tropical climates could be elevated higher on concrete blocks to improve airflow beneath the structure and reduce flooding risk. July 1941. The first complete prototype went up at Quonset Point in 16 hours. 6 men with hand tools and a simple instruction sheet assembled the structure from crated components. Naval observers watching the test struggled to process what they'd witnessed. Traditional military construction took weeks with skilled crews. This building appeared in less than 1 workday. The test continued. The crew disassembled the hut, loaded components on trucks, moved everything half a mile, and reassembled it in 14 hours. The building was genuinely portable. The Navy approved the design in September, and immediately ordered 5,000 units. Then December 7th happened. Pearl Harbor transformed orders from 5,000 to 50,000 to eventually more than 150,000 units. Production ramped up across 36 manufacturers. These weren't specialized defense contractors. They were companies that normally made grain silos, water towers, industrial tanks. Firms like Strand Steel Corporation in Indiana, Great Lakes Steel in Michigan, they already owned the equipment needed. Massive sheet metal presses, industrial bending machines, punch presses for drilling holes. Converting production lines to Quonset manufacturing took weeks. The manufacturing process embraced simplicity. Steel sheets arrived from mills pre-cut to size. Presses stamped out identical arch sections. Panels arrived pre-insulated. Windows and doors came pre-hung in wooden frames. Everything shipped in crates ready to bolt together. No custom fitting, no on-site modifications, no craftsman decisions, just assembly according to simple pictorial instructions that required no written language. By late 1941, production exceeded 100 huts daily. A new, complete building every 14 minutes during an 8-hour shift. But the real test came when these structures confronted the environments they were designed to survive. The Iceland deployment provided the first brutal field test. 8,200 Quonset huts shipped to Iceland in late 1941. The island sat just below the Arctic Circle, subject to hurricane-force winds, freezing temperatures, and weather that changed from calm to catastrophic in minutes. The November gale that destroyed PBY flying boats and tore apart Nissen huts left Quonset standing. But understanding why required examining the physics of wind load on curved structures. When wind encounters a flat surface, it creates pressure. The force pushes directly against the surface, concentrating stress at connection points. Traditional buildings with vertical walls and flat roofs fight wind through brute strength, thick walls, heavy foundations, structural reinforcement. The Quonset's curved form approached wind completely differently. When air hit the curved surface, it flowed around the structure instead of pushing against it. The smooth arch created minimal turbulence. Wind pressure that would concentrate catastrophically on corners and edges distributed evenly across the entire curved surface. The arch geometry converted wind force into compression load on the structure itself. The stronger the wind, the tighter the arch compressed, actually increasing structural stability. The building didn't resist the wind through strength. It redirected wind force through geometry. The Iceland storm vindicated every design decision. The corrugated steel panels flexed slightly under extreme wind but didn't tear free because they were attached at multiple points along wooden purlins. The arch ribs transferred load continuously to the base. The structure behaved as designed, yielding slightly under stress, but never failing catastrophically. Temperature presented the next challenge. Iceland tested cold performance. Arctic bases in Alaska tested extreme cold. Tropical deployments tested heat and humidity. Desert installations tested temperature extremes in both directions. The original Quonset design included 1-inch wood fiber insulation. In Arctic conditions, this proved marginally adequate for structures that included heating. Units deployed to Alaska and the Aleutian Islands received enhanced insulation packages. Some installations used double wall construction with additional insulation layers. Others employed earth berming, piling soil 3 to 5 feet high against the exterior walls. The berming technique served dual purposes. The earth provided additional insulation, and it protected against bomb blasts. Explosions that would shred an exposed structure simply displaced soil around a bermed Quonset. The arch shape meant blast pressure rolled over the top instead of concentrating against walls. Engineers discovered the curved roof shed snow naturally. The smooth metal surface provided no purchase for snow accumulation. Even in regions receiving 20 feet of snowfall annually, Quonset stayed clear through natural shedding. This eliminated the roof collapse problem that plagued traditional buildings in heavy snow regions. Tropical deployments revealed different challenges. In the South Pacific, temperatures regularly exceeded 100 degrees, with humidity approaching saturation. Steel structures without proper ventilation became uninhabitable ovens. Condensation formed on interior surfaces, dripping constantly, rusting equipment, rotting supplies. The Navy developed tropical variants with enhanced ventilation, additional louvers in end walls, larger ridge vents. Most importantly, raised floor systems. In Guadalcanal, New Guinea, and Philippines installations, Quonsets sat on concrete blocks or pilings elevated 2 to 3 feet above ground. Air circulated beneath the floor, dramatically reducing interior temperatures and preventing flooding during monsoon rains. The curved roof shape that shed snow in Alaska also deflected tropical downpours. Rain didn't pool on flat surfaces. It ran off immediately, reducing leak potential and preventing water infiltration around fasteners. Rust became the primary maintenance issue in tropical climates. The original Quonsets used low-grade steel that corroded rapidly in saltwater environments. By 1943, production shifted to rust-resistant galvanized steel. This extended service life from months to decades in harsh coastal conditions. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Typhoon conditions provided the ultimate tropical test. In 1962, Super Typhoon Karen struck Guam with sustained winds exceeding 170 miles per hour. The storm destroyed traditional wooden buildings across the island. But contemporary reports noted large numbers of Quonset huts remained standing. The arch shape and lack of roof overhangs allowed wind to flow smoothly over the structures. The same aerodynamic principles that worked in Iceland worked in typhoon conditions. Combat zones tested blast resistance. The Navy specified arch shape partly for shell fragment deflection, but nobody knew how well that would work until Quonsets entered combat areas. In Pacific Island campaigns, Quonsets served as field hospitals, supply depots, and command posts near active fighting. Japanese artillery and air attacks targeted these installations. Engineers discovered the curved steel surface deflected shrapnel more effectively than flat walls. Metal fragments that penetrated flat-sided structures simply glanced off curved surfaces or punched through without causing catastrophic structural failure. A hit that would collapse one wall of a traditional building might penetrate a Quonset skin but leave the structure standing. The toma, corrugated panels, could be patched with metal sheeting. The arch ribs transferred load around damaged sections. Individual arch sections could be replaced without dismantling the entire building. This damage tolerance proved crucial in forward areas. A field hospital that could sustain nearby explosions without collapsing meant surgeons could continue operating while under attack. Supply depots could take hits without losing entire inventories. The structures weren't invulnerable, but they were remarkably resilient. The most extreme test came from direct bomb impacts. Heavy steel Armco variants of the Quonset design were specifically engineered as ammunition bunkers and air raid shelters. These used 8 to 14 gauge heavy iron instead of standard corrugated steel. Units could be buried up to 6 feet underground with earth cover. The arch geometry proved ideal for buried applications. Soil loading compressed the arch, but that compression increased rather than decreased. Structural stability. The curved form distributed earth weight evenly. Traditional rectangular bunkers required massive internal bracing to prevent wall collapse. Arched bunkers were self-supporting. One field report described a buried Armco Quonset that survived a near miss from a 500-pound bomb. The explosion cratered the ground 15 feet away. Shockwaves displaced tons of soil, but the structure itself, though partially uncovered by the blast, remained intact. The arch had absorbed and redistributed forces that would have flattened a conventional bunker. This resilience wasn't accidental. The Navy's initial specifications demanded strength and fragment deflection. Brandenburger's team delivered both through careful application of structural principles proven over centuries of arch construction. The Roman Pont du Gard aqueduct, built in the 1st century, still stands because its stone arches distribute weight through compression rather than bending. Gothic cathedrals soar hundreds of feet high using flying buttresses that are essentially external arches, redirecting roof loads to ground level. The Quonset hut applied these same principles using modern materials and prefabrication techniques, but understanding why the arch worked required examining forces at the component level. A flat roof under snow load bends. The top surface goes into compression, trying to shorten. The bottom surface goes into tension, trying to elongate. This bending creates shear forces that can tear the structure apart. The only solution is making the structure strong enough to resist bending through sheer material strength. An arched roof under snow load compresses. The entire structure squeezes together like a spring. Compression forces travel through the arch to the foundation. As long as the arch maintains its curve, and the foundation prevents the base from spreading, the structure can support enormous loads without bending. The Quonset's corrugated steel skin added another layer of strength. Corrugation itself is a form of arch. Each ridge and valley creates a tiny arch running perpendicular to the main structural arch. This corrugation dramatically increases rigidity without adding weight. A flat steel panel bends easily. The same steel corrugated resists bending through geometric stiffness rather than material strength. The arch ribs and corrugated panels worked together as a composite structure. The ribs provided the major load paths. The corrugated skin distributed loads between ribs and prevented local buckling. The wooden purlins that attached panels to ribs tied everything together into a unified structural system. This integration meant damage to one component didn't cause cascade failure. A panel could tear without affecting adjacent panels because each attached independently to purlins. A damaged rib could be bypassed as loads redistributed to adjacent ribs. The structure degraded gradually under extreme conditions, rather than collapsing suddenly. Traditional military buildings failed catastrophically. A wall breach could trigger collapse of attached roof sections. Fire could spread rapidly through wooden interiors. Artillery hits often destroyed entire structures. The Quonset's all-steel construction and segmented architecture provided resilience traditional construction couldn't match. Field modifications demonstrated this flexibility. In some installations, crews connected multiple Quonsets end to end, creating long corridors. Others placed units side by side and cut openings through the walls, creating large open spaces. The arch structure adapted to these modifications because loads distributed around the alterations. Engineers also discovered the buildings could be relocated. Units assembled at one location could be disassembled, transported, and re-erected elsewhere. The bolted connections allowed complete disassembly without damage. This mobility proved valuable as campaign fronts shifted. Infrastructure moved with advancing troops. The Seabees, the Navy's construction battalions, became expert at rapid Quonset deployment. 10 men could erect a standard 20 by 48-foot unit in a single day using only hand tools. Larger warehouse models required more crew but still went up in days rather than weeks. One Seabee battalion developed a particularly clever technique for Pacific Island operations. They poured concrete foundation slabs at one location while erecting hut frames at another nearby site. Once the concrete cured, they literally picked up complete frame assemblies and hand-carried them to the dried foundations. This parallel processing dramatically accelerated construction schedules. In Alaska, civilian contractors developed sled systems for relocating assembled Quonsets across frozen ground. They bolted steel sled runners to the floor framework, creating mobile camps nicknamed Wannigans. Entire installations could be moved to new locations without disassembly. This versatility stemmed from the fundamental design simplicity. The building was essentially a kit of standardized parts: arches, panels, floor sections, end walls, all interchangeable. A damaged component could be replaced with an identical part from any manufacturer. No custom fabrication required. By 1943, manufacturers had refined the design into what became known as the strand steel variant. This version used lighter gauge, galvanized steel, half-inch plywood floors instead of 1-inch tongue and groove, and a modified panel layout that allowed flat shipping instead of pre-curved sections. The weight reduction was significant. The strand steel hut weighed 35% less than the original design while maintaining equivalent strength. This made shipping more efficient. A standard 20 by 48-foot unit weighed approximately 7,000 pounds. One truck could haul an entire building. Shipping considerations drove many design decisions. The military needed structures that could travel by cargo ship, land on invasion beaches, fly in transport aircraft, or traverse roadless terrain. The crated Quonset met all these requirements. When crated for shipping, a standard unit fit in 12 crates, weighing a total of 3,200 pounds. The strand steel redesign reduced this to 3 crates, weighing 2,500 pounds total. Compare this to the shipping requirements for traditional barracks materials: lumber, concrete, windows, doors, roofing, all requiring separate packaging and totaling tens of thousands of pounds. The shipping efficiency multiplied across thousands of units. The U.S. Army calculated that deploying Quonsets instead of traditional construction materials to Pacific theater bases saved approximately 3 million tons of cargo ship capacity between 1942 and 1945. That represented roughly 150 Liberty ship voyages freed up to carry ammunition, vehicles, and fuel instead of building materials. The logistics advantage compounded when structures reached their destination. Traditional construction required skilled carpenters, concrete workers, electricians, plumbers. The Quonset required warm bodies capable of following pictorial instructions and using basic hand tools. Any infantry squad could become a construction crew. This labor flexibility proved crucial as the war expanded. Skilled construction workers were needed for complex projects: airfields, docks, bridges, fortifications. Using them to frame barracks wasted their expertise. Quonsets freed skilled labor for tasks that actually required skill. The standardization also simplified supply chains. Instead of ordering lumber, nails, roofing, windows, doors, each requiring separate suppliers and specification, logistics officers ordered complete Quonset units. One requisition, one supplier, one delivery. The building arrived as a system rather than components. This integration extended to interior configurations. The Navy designed 86 official variants for different purposes: barracks sleeping 12 to 16 men, medical dispensaries with examination rooms, dental clinics with equipment mounting points, laboratories with ventilation systems, mess halls with kitchen equipment, repair shops with tool storage, warehouses with loading doors. These variants used the same basic structure with different interior partitions and equipment. A barrack could become a hospital ward by installing different partitions. A warehouse could become a mess hall by adding kitchen equipment. The flexible open interior accommodated changing needs without requiring new construction. This adaptability mattered enormously in military operations, where requirements shifted constantly. A base initially housing garrison troops might suddenly need hospital capacity after a major offensive. Traditional construction meant building new specialized facilities. Quonsets meant reconfiguring existing structures. The standardization also simplified training. Once personnel learned to assemble one Quonset, they could assemble any variant. The core process remained identical: erect arches, install panels, attach end walls, complete interior. Specialized variants just added specific interior elements. By 1945, American military installations worldwide housed millions of personnel in Quonset structures. The buildings functioned in every climate, from Alaskan permafrost to equatorial jungles, from North African deserts to North Atlantic islands. The accumulated field experience revealed both strengths and limitations. The structures excelled at their designed purpose: rapid deployment, extreme environment tolerance, minimal maintenance, combat resilience. They provided adequate rather than ideal living conditions. The curved walls reduced usable floor space. The metal construction transmitted sound poorly, making interiors noisy. The standardized design offered no aesthetic appeal. But wars aren't won through comfortable accommodations and beautiful architecture. They're won by getting resources to the right places at the right times. The Quonset hut succeeded because it solved the fundamental logistical problem of housing millions of troops across 6 continents in less time than traditional construction could house thousands. The engineering achievement lay not in revolutionary new technology, but in brilliant application of established principles. The arch was ancient. Prefabrication was understood. Metal construction existed. Brandenburger's team succeeded by integrating these elements into a system optimized for mass production, global logistics, and operational flexibility. The Iceland storm that crushed PBY flying boats and destroyed Nissen huts taught engineers that curved structures survive where flat structures fail. Tropical deployments taught that ventilation matters more than insulation in hot climates. Arctic installations taught that berming protects better than additional insulation. Pacific combat operations taught that damage tolerance beats absolute strength. These lessons accumulated into a body of knowledge that influenced post-war prefabricated construction worldwide. Modern manufactured buildings, modular construction systems, disaster relief shelters all descend intellectually from the Quonset concept. Standardized components, rapid assembly, environmental adaptability. The military continued using variations of the arch design through subsequent conflicts. Korea, Vietnam both saw updated versions of the basic concept. Modern deployable shelters use advanced materials, aluminum instead of steel, synthetic insulation, computerized climate control, but the fundamental approach remains unchanged. Prefabricated sections, rapid assembly, complete portability. Some original World War II Quonsets remain in service 80 years later. On military bases, at research stations, on farms, serving as workshops, storage buildings, even homes, the longevity speaks to the design's fundamental soundness. A structure engineered for temporary wartime use proved durable enough for permanent applications. The question that began this examination, how did such a simple structure survive conditions that destroyed more sophisticated buildings, finds its answer in the physics of the arch and the intelligence of integrated design. The arch survives because it doesn't fight forces, it redirects them. Wind becomes compression. Snow becomes compression. Even blast waves compress rather than break the structure. Physics works with the design rather than against it. The integrated design survives because every component serves multiple functions. The corrugated skin provides weather protection, structural stiffness, and panel attachment. The arch ribs carry loads, mount panels, and define interior space. The end walls close the building, provide access, and allow. Climate adaptation. Nothing is purely decorative or single-purpose. This efficiency of design, where every element contributes to multiple performance requirements simultaneously, represents genuine engineering elegance. Not elegance in aesthetic terms. The Quonset was never beautiful, but elegance in functional terms. Maximum performance from minimum components using optimal geometry. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.